Alright, welcome back to the pycse channel. Yesterday I talked about some rules with array broadcasting and how they work and what you can do with them, and after that I thought maybe we should try an actual application where you could see why it's so valuable and so important and worth learning. So what I'm going to do today is exactly that kind of application where we have over here in this little figure, say 3 points, P0, P1, and P2, and what our assignment is to calculate those distances, the distance between 0 and 1, and 1 and 0, P0 to P2, and vice versa, and P2 to P1. So that distance matrix is common in things like molecular simulation, where these might be bond lengths between atoms, or it could be in a travel. If these are points on a map, it's the distance that you have to travel, and it's often a need to calculate all of them. So I'm going to take three approaches that lead us to using array broadcasting to do this, so that it's really clear what the benefit of it is. Now, the first thing we'll do is just the old-fashioned, what I would call an old-fashioned loop. And that is, let's just make our array. Let's import NumPy. And make an array. Let's let Python start up here. X equals np.array. And we'll put in the 3 points. So those 3 points are 0, 1, 0, a half, and 1, 0. All right, so 0, 1, 0, comma 1 half. Let's just put in 0.5, and 1, comma 0. Okay, and then we have to close this. And let's go ahead and plot it just to make sure things look okay. Plot.plot. And we'll do this kind of fancy syntax where we unpack the transposed array so that we have 2 rows. And we'll just have a look and make sure that the plot looks like we expect. Okay, so here are the 3 points drawn like that, and off the top of our head, we should be able to see this distance is a half. That should be pretty clear. And then this distance should be the square root of 2. So 1 squared plus 1 squared is 2, and we take the square root of it. And then this distance will be root 5 over 2. And so we have some idea that we know what the answers are here. And that's helpful because it gets more and more difficult to figure out whether we've done the right things. Okay, so let's do this the old-fashioned way. Let's look at x.shape. This shows us that we have 3 rows and 2 columns. So let's define these as some variables. And then let's make an empty array. So let's say d is equal to np.full. And the shape is going to be 3, 3, and I'm going to fill it with not a numbers for now. So we're going to eventually fill in these values, and it's convenient to see that we got all of them as we go through our loops. Okay, so we'll do, say, for I in range of n. That will iterate through each pair of points, and then for j in range of n. So we're going to find every pair of points ij. We will define the ij element of this array as the np.linalg.norm. That's the way we'll calculate the distance of x of I minus x of j. All right, so this is the ith point of x is the ith point. This is the jth point. We just subtract them and find the magnitude of that vector. That is the distance between all of those points. And when we run this now, we should see this array where you see zeros on the diagonal because that's the distance of point 1 or point 0 to point 0, point 1 to point 1, point 2 to point 2. Of course, those are 0. And then we have 1/2 and 1/2 for these two. And you see the square root of 2 and the square root of 2. And then 1.118 is what? That is the square root of 5 divided by 2. Like that. Okay? So that's this old-fashioned way of using iteration to calculate all of the distances between these points, this point, and this point, and get it into the symmetric array. And you can see we don't have any not of numbers left, and that means that we were able to hit every single point in the right way. If you used 0, then it would be less obvious because we have zeros on the diagonal, and then you might not necessarily know whether you actually calculated a 0 or it's left over. And similarly, if you used 1, you might not know if a distance was actually 1 or if you calculated 1. So the only answer that really makes sense otherwise would be like -1, because you know no distance could be -1. Okay, so that is the old-fashioned way of doing it. It's a double loop, and loops are kind of notoriously slow when they get really big, and we would like to leverage the element-wise operations in NumPy to be able to do this. So to get there, we have to start thinking about arrays and element-wise operations. So let's switch and work on something on paper for a little bit and see how we could think about doing this. So we have here the problem set up. We have our X array, and I have labeled them here as P0, P1, and P2. That is like right here. And what we want to do now is start to think about how could we define the distances between these, where we're going to end up calculating this array down here with these distances. Now the X array is a 2D array. It has 3 rows and 2 columns, so that's the shape that I have right here. And we would like to work out a strategy for doing this all with arrays and not with loops. So let's write out one way we could think about this. So if I could say schematically write an array that was say P0, 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 P1, 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 and P2, 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 right? Where I just take the array of P0, P1, P2 and repeat it so that it goes column-wise, and we have this array. And then if I could construct a second array that had them in the other order, P0, P1, P2, like this, then this one has this row, and this one, so whereas the one on the left is kind of repeated to the right, this one is repeated going down. If I could just subtract this, then what the element-wise result would be over here would be like V00, V01, V02, V10, V20, V11, V12, V21, and V22. So this matrix on the right is the element-wise difference of P0 minus P0 for V00, P0 minus P1 for V01. And a couple of things we should note here is that even though I've drawn these as two-dimensional arrays, each one of the P's is actually a two-dimensional array itself. So this is a three-dimensional array, and it has a shape of 3, 3, 2. And this one has 3, 3, 2. And this one is 3, 3, 2. So what are these dimensions, right? If we call this one x1 and this one x2, then if I say x1 of say I comma j minus x2 of I comma j, remember these are done element-wise, so the i's and the j's are the same, then this is basically p sub I minus p sub j. And it is a 2D vector that we can find the magnitude of. And what we want, and so this over here is basically Vij, or in the indexing notation, like this. And what we want is the length of this little v sub ij, so we really want np dot linalg dot norm of v I comma j. And what that means when we write it like this is that we want this along axis equals 2, right? So this is axis equals 2. It's the last one. This one is axis equals 1 or 0, and this one is axis equals 1. All right, so I've kind of laid out here the strategy that we need to take the array of p0, p1, p2, construct x1, construct x2, subtract them, and then we're going to take the norm of the result along axis 2, and that's going to lead to a 3 by 3 matrix that contains all of these distances. So let's talk a little bit about how we can construct x1. If you look at x1, it is taking 3 copies of x and stacking them along the way that makes columns, so that is stacked on axis 1. That is, it's the second axis in here that we're stacking them along. And then when we look at x2, x2 is the same idea. It is 3 copies of x, but they're stacked going down. So they're stacked along the first 0th axis, which is the rows. Okay, so if we look at np.stack and use them to create x1 and x2, then we should be able to do all of this algebra like I've just shown here and get the same result as we got from the loops. So let's go check it out. All right, so back over here, now we're going to try element-wise algebra. So going back, we have, this is the array of x. So let's say that x1 is equal to np.stack 3 copies of x, and I said this one should be axis equals 1. All right, and let's see what we get. So it looks like this. You can see that there are 3 sets of these, and let's look at the shape. The shape is, as I advertised, 3 by 3 by 2. And what we should do is take some time to inspect this, and let's look back here and see what we should see. That in x1, if we look down the first column, we should see p0, p1, and p2. So we should be able to do some indexing and show that those are the cases. So let's try it out. So I said the first column, so that means that is going to be, let's put some brackets, that's going to be something, comma 0. And let's look at 0, 0 just to see what gets indexed out. This turns out to be p0. And if I go down to the second row, we get p1. And this third row gives us p2. So that makes sense. And then if we go across here, this is p0, and this should be p0, and this is p0. So going across the row is always p0, and going down the column gives us those p0, p1, p2. All right, perfect. Now let's make x2. So we said x2 is the same idea, but stacked along axis equals 0. And let's have a look there. So here you see this structure with x2, we get a different structure. So this looks like a copy of the x vector along these. And let's go back and look at what x2 should be. So over here, x2 should be p0 down the first column and p12 along the first row. All right, so we have here, let's look along the first row first. So if we look at this, we should get p0, and that's what we get. And for the next one, it should be p1, and for the next one, it should be p2. And if we go again back to the origin, we get p1. If I go down the rows now, so this is the second row, should be the constant, and that should be a constant. So that looks okay. And now we should be able to do the algebra that I described. So let's now just look at x1 minus x2. So this is going to element-wise subtract all of these. The shapes are perfectly aligned, so we have a 3 by 3 by 2 array, and what we get is the difference here like this. And let's look at the shape just to confirm that it is 3 by 3 by 2, and that's what we see. So now what we want to do is take the norm of each element along axis 2. So we just wrap this in np.linalg.norm. We're going to take the norm of this difference and apply it to axis equals 2. And that's going to compress this from 3 by 3 by 2 into a 3 by 3 array. And it is the actual distances then, because what we've done here is calculate the norm of x1 minus x2 along axis equals 2. So that's the norm of each one of those elements, and we get our distance array like we got before. We have the halves, the square roots of 2, and the square root of 5 over 2 that come out of that. Now, if it feels like we did a lot of work to avoid writing the loops, you're correct. It is necessary to do several things. One, you have to construct these arrays, and if x was very large, then this would take up potentially a lot of memory. And if you, let's see, if we had to do more than 3, then you need as many points here as copies as you have points. So it can be a little bit inconvenient if x was, say, 1,000 points, then you would have to make 1,000 x's. And there are some ways to do that, but I'm not sure it's like super interesting to get into. Okay, so what about this array broadcasting, right? So array broadcasting is the trick that we looked at for making this super nice syntax. So let's take a step here and say now with broadcasting. So what we wanted to do was take the x array and then find all the differences with all the other elements in the points. And so the simple way of doing that is like this. We say x colon comma none. So we're going to expand it in one direction and subtract x none comma colon, where we expand it in the other dimension. And this already gives us that difference array that we were interested in. So this is already the difference of all points of P with all other points of P. And now we can just wrap this in the linalg.norm. And we still have to do axis equals 2, like this. And we now have in one line the distance matrix that we were looking at. And this is the syntactic sugar that broadcasting is used most commonly with, is so that we can avoid all of the loops that we did in the first place and making all the copies that we made in the second case. And it's the trade-off is it's very unintuitive what this actually expands into. So we can take a look at that if you're trying to debug and see what is this. So again, let's start with x. X is just the 2D array of our points. If I add this, it just puts, maybe we should it just puts an extra layer of brackets around it, but it doesn't change the shape to be quite right yet. What it does is it adds a 1 in the middle here. So it adds a new dimension after the first one and before the last one. And it's not clear what this should expand to. So we can find out though if we use np.broadcast2, and we'll copy this. And remember, the broadcast rule says that anywhere there's a 1, it can be broadcast into a new shape. And so we'll broadcast it into the shape 3 by 3 by 2. And what that's going to do is make the copies along this axis equals 1 case. And it gives you this result that we saw before. And if we do the same thing with the, let's just reverse these. This puts a new axis at the beginning so that it's going to broadcast along the rows. And so that gives us this version. And so that's actually what's happening when we do this like super fancy syntax up here, is that you add a new dimension on the second on axis equals 1, which makes it expand along the columns. And you add a new dimension here, which makes it expand along the rows. And so each one is expanding into the copies of the arrays that we made above. And it's just doing it in this very, very terse, concise manner. And it doesn't matter what order you do these things in. The expansion works either way because we're just doing a difference here. And now that I said that, it doesn't. Oh, we have to do minus. So it doesn't matter which order you do it in, because the subtraction doesn't change anything that you're doing. Sometimes it does matter, and it all has to do with how the shapes align and what you're doing. So that's really it for today. We looked at a couple of different ways to solve this particular problem, where we wanted, in this case, a distance matrix that is symmetric for all of these distances of the points. One way you can get there is this loop, where you iterate over all of them and work it out. Another way is you construct the arrays that you need and then do element-wise operations, and then finally do like a condensation of the norm across this. And then finally there is this way that doesn't require any of those intermediate variables. It just directly expands the arrays in the way that you want that way. So there are other ways you could do this. I chose np.linalg.norm mostly because it is a one-line way of doing it. But let's take one more look at something else we could do if you wanted to think about something that is like more obviously the distance. So here what we need is the magnitude of each one of these. So the usual way of doing this would be to square each of the elements, and then we want to sum along here and then take the square root of that. So we could say np.sum. Again, we need to sum along axis equals 2, and that gets us down to a 3 by 3, and then we have to take the element-wise square root like this, and you get to the same answer as before. So this is more like distance equals np.square root of the sum of elements squared. So this is essentially what np.linalg.norm does. It just does all of the summing and squaring and everything in a cleaner way. All right, that's it for today. If you like this topic, go ahead and like the video. Maybe subscribe to the channel or tell some people about it. And until next time, I will hope you have a good time using NumPy and array broadcasting, and I'll see you later.